Okay, so hello, my name is Helmut Hlavacs. I am professor for computer science at the University of Vienna. And our talk today is a continuation of our presentation from last year, where we talked about teaching the Vulkan API to university students with applications in Vulkan video. And today we want to give you an update because both topics have actually sparked some interest. We want to give you an update. In my part, I will focus more today on didactical information, didactical ideas of what I use when I teach the Vulkan API and what I think is important and very helpful. So I've been teaching the Vulkan API for 7 years now for university students. And these are the courses that we offer. Here we have the courses that focus on the Vulkan API, but before students can actually enter one of them, they have to go through another course, which is more on the foundations of computer graphics. So this is very theoretical. They have to come up with a ray tracer on the CPU. So this has nothing to do with Vulkan. But once they are through that, they can do any of these courses. And we have one course that actually focuses very much on Vulkan. So here we really go and teach the API to the students who have absolutely no experience with this. So they are totally newcomers. And here as a basis, we use the Vulkan tutorial. I will come back to this later on. And with the other courses, they have a different focus, but here we provide game engines, teaching game engines that are based on Vulkan. So whenever they use them, they are kind of forced to use Vulkan also and go more into the depth of Vulkan. But today I really want to focus on teaching this a basic course on Vulkan, which is called Real-Time Computer Graphics. And I really want to delve more into what I think works when you teach Vulkan to students. And concerning the organization of the course, I think there are a couple of things that are very important. Among them is repeatability and communication. So what do I mean with that? So communication, of course, is important. We have a Moodle page where we convey all the information about the courses, but also we have a forum, and we encourage students to post questions because they're supposed to program a lot. So this is an implementation intensive course. So students are required to program a lot. And when they have problems, they have all kinds of hardware and software where they're implementing. They have Linux, they have Mac, they have PC. And they will run into problems. So when they have a problem, when they really cannot continue, post a question in the forum, and then the teachers will try to solve it. But if you're really having some kind of minor problem, then the second part of the communication is that we encourage also the students to help each other. So this is very important. Even if you're supposed to solve all of this by yourself, we encourage students to help each other and show each other source code that actually works. And the other thing that is, I think, also important is recording the lectures, because in the lectures, there's so many details, so many calls that you have to go through, and the parameters and why this object is there. That is not enough to have to give the lecture only once. So every lecture is recorded. We put it on the Moodle page, and students can rewatch it whenever they like. So concerning to the didactics, there are things that work and there are things that certainly don't work. And let's start with the things that certainly don't work. And that's it's kind of putting too much theory on the students. So like going through every detail in the specifications, going from specification 1.0 to 1.4 and going through all of the extensions and so on, that really doesn't make much sense. So too much theory, too much unnecessary theory, we try to avoid that. Too fast progress, also not very good, because people need time to reflect on this. People need time to play around with the content, make it their own, and kind of form a habit of using stuff. And if you really overload them with theory, you confuse them instead of letting them learn. So instead of having a theory overload, we try to focus on a smaller subset that actually makes sense, and that gives them also the opportunity to build on this subset and go beyond that when they choose to. So we need some kind of a slow progress. We have a lot of programming going on. and every week or every other week they get new tasks to solve. And so they will learn by implementing stuff and playing around with stuff, making this actually a habit. So you should be acquainted with a physical device or a logical device or descriptor sets and so on. So you need time to play around with that. Of course, students need also some kind of guides and stuff to bootstrap them into the Vulkan API. And I like to use something that's called scaffolding. So that's something that actually provides them a working way, a very simple implementation that gets them from start to finish. So from creating an instance to rendering an object or rendering a triangle, you'll find everything into this very small, thin layer of a scaffold. And then we go through this piece by piece and understand what's going on. And so this is existing code. And the idea is then to work on this code, change it, adapt it, understand it, and gradually make it your own, gradually own it. And then you can add new functionality. And I will come to this in a moment. So starting from this base, students are supposed to understand the base and then extend it. And then finally, in the last slice of the course, to create their own game engine on top of that and create their own game with that. Again, a lot of programming, a lot of implementation, but you cannot do this if you haven't understood the basis where you're actually coming from. As an important learning tool that I've always cherished actually is the Vulkan tutorials. Probably everybody knows that. It was first a standalone tutorial, then it was also incorporated into the Khronos webpage. And what I always liked about the tutorial is this is a kind of a central function that you call. It's called init Vulkan, and then you go through all of these steps. And you can see the intent of what's going on, but you don't see the implementation details here. So create the instance, create the surface, and so on. And I always like this because it gives you an overview of what's happening, but it doesn't overflow you with unnecessary information at this time point. There are a couple of problems, of course, with the Vulkan tutorial nowadays. It's a bit dated. And if you think about this overview here, you really don't see what's going on inside of the functions, and you don't see what type of state they are actually working on. So that would be very nice to turn them into pure functions where you give input parameters and you get an output. And what that enables you is you can directly use this and put it into your own game engine and connect it to your own game state. So also what you don't see is that functions calling other functions working on the global state. So something like here, you have a function calling other functions working on the global state. So you get something like this. You have a lot of complexity going on and you lose the oversight of why you're actually working on a specific state. So instead, I want to turn this into something like this, where you have here a layer that discloses the intent. So this is what I want to do, but there is no implementation here. And then you simply call implementation functions, just like the tutorial does, but with the certain parameters, input and output parameters. So the implementation does not have any direct influence or access to the state. It just get input and output parameters. This leads me to the adapted tutorial, which I have created now for the teaching. It is based on the Vulkan tutorial, and I adapted it a little bit and made it more modern because these are the goodies that you actually have in the SDK anyway. So I added a couple of stuff, SDL2, ImGUI, VMA, Vulk, Slang. We're going full speed Slang now because I think this is really the future, and so all of the shaders will be moved to Slang. And this is what the init function now looks like. It looks a little bit more difficult, more complicated, but it's essentially the same functions. Here we init VMA, here we set up ImGUI, and here we have another function that creates objects, and now we can create more than one object. And it's very simple, so it's a really very thin layer on top of the tutorial. And now actually you can use all of these functions in your own game engine. You can take them over, you can adapt them, you can change them at the functionality, you can add more parameters if you want to extend the functionality and so on. Now this is the tutorial. This is really a very essential tool when we teach Vulkan. But we have other courses that use a more sophisticated game engine. So I'm currently working on the next iteration of the Vienna Vulkan engine, and it will follow very similar ideas. So it will have some kind of an intentional layer, the systems, and the systems are simply classes that are completely isolated from each other, so that you can really focus on what's going on in one system. But systems are not allowed to call each other. Instead, they have only a private interface. And when they want to interact, they send each other messages. So you can actually switch on and off messages. And so you don't have any indirect interaction. Instead, you have a helper layer where all of the implementation stuff is happening. And here, then I can switch from 1.0 specification to 1.3, from C implementation to C++ implementation, and give the students these the different variations of what they should learn. And finally, of course, at the end, students are supposed to take over the tutorial, create their own game engine, very simple game engine. This is not about very complicated stuff, but just to be able to do something with that. And that's the fun and the creative part. These games have been created last year in the summer semester. These came all from the tutorial, and on top of that, then students created their own games. And finally, I want to also talk about the different needs between university students and tech engineers, because we've been teaching university students, so really want to give them a broad spectrum of computer graphics, real-time computer graphics. And the Vulkan API is just one part of that, even though it's quite extensive, of course. But if you go to tech engineers and teaching tech engineers who have no knowledge about Vulkan, then probably the curriculum will look quite differently, because a tech company is not really interested in color theory or something like that. So I've been thinking about what would be interesting for tech companies if they have newcomers and you want really to get them into the Vulkan API. What would you like to teach them as a bootstrap? So I would be interested in your ideas and your comments about that. Finally, here are a couple of links. The adapted tutorial on my GitHub. I have also all of the lectures recorded. Every year I record all the lectures. This is the introduction to Vulkan API. If you're interested, you can watch it on YouTube. If you want all the other lecture videos, just send me an email and I will send it to you. Thank you for your attention, and I will hand over now to my colleague.
Hello, my name is Bernhard Schrenk. I'm a student at the University of Vienna. I apologize for the layout of the slides. It seems we have some problem with the font, but I think you can read everything. So I was here on Vulkanised last year and talked about my projects at the University of Vulkan Video, and from that, I started to find a topic for my thesis, and what I tried is can we implement the Vulkan video extensions to purely run on the CPU? So why does someone need that? Apart from an academic point, is it possible? Yeah, if you want to use it in a continuous integration in a test setup, it would be quite interesting to have Vulkan video running, even if you don't have the hardware. If you run it on a legacy system, as you can see in this screenshot, in visualization systems which need to stream or create videos out of these visualizations, even if this hardware is not capable of doing video encoding, it's interesting to have this possibility. So we quickly surveyed what are the other options, and of course you can use other codec APIs. Some have software fallbacks, but there's no other than Vulkan Video, which is vendor and operating system independent. There's only missing the software fallback. And the other reason why you would use Vulkan Video is you have this tight integration with the graphics API. You have synchronization, which works for both. So you can have zero copy, you have low latency possibilities for game streaming, video textures, as you can see here in the Vienna Vulkan engine with the video texture support, and many other possibilities. So then we asked us where to begin this project, and we decided, yeah, let's go with a basic subset. We want to have H.264 baseline profile encoding for the first version. And we had to build on top of any existing CPU-based Vulkan Video implementation, because we did not want to implement a full Vulkan stack. And we decided to try it with Mesa 3D Lavapipe, which is a CPU-based rasterizer, so it's completely running on a CPU. Here you have a quick overview how it works. You have the Vulkan API, which is implemented by Lavapipe, which is a front-end component of the Mesa driver, which then utilizes LLVM pipe as the rasterizer itself, which has also other interfaces like OpenGL. LLVM pipe generates rasterizer and shader code in LLVM intermediate representation, and then uses LLVM finally to create a native meshing code and run it on your CPU. So it's faster than pure software interpretation. Of course, much slower than doing that on hardware. And we thought, okay, we need to implement on one side the Vulkan Video extensions. And as we do not want to implement also the codec, we need an API and then plug in some existing open source codec on the other side. So this was the goal to go. And short about the Lavapipe project. If you don't know it, or it's within the Mesa driver. It's available on Windows and Linux, and it can provides you full Vulkan API 1.4 compliant without any hardware support. So of course a CPU, but no GPU. And it's great for such experiments because you don't have many dependencies. You can compile it easily. And if you want to have a look into it, on the right side, you see the interesting subdirectories in the Mesa repository, where you find the code pieces which build finally the Lavapipe driver. So what did we need to add to get this working? On the Lavapipe side, of course, we need new feature queries for all the Vulkan video features. Then there is some special part in Lavapipe. It is mainly in the Mesa driver in the core. For Vulkan, it it automatically generates out of the specification, a Vulkan specification, using an C code generator, which is written in Python, all the handling for the command buffers. So parsing them, copying them when you submit to the queue is done in this automatically generated code. On the other side, most of these commands are easily copyable, but the Vulkan video use deeply nested structures with pnext and quite heavily using this feature, which the other commands not are really doing that. So we had to extend this code generator to understand the Vulkan video specification also. This enables now Lavapipe to understand every part of the specification, of the Vulkan specification. And finally, Vulkan Video also has new query pool types. Also, this was needed to be extended. And deeper in the chain, video always uses other image formats. You have the multiplane images everywhere, YCPCR in 2-plane or 3-plane. All this was needed to be extended, that it works. And finally, you have session support for video sessions, and then implement every video command in which can be handled by the queue. And the other problematic part was Vulkan Video is more or less stateless. So you need a codec which is stateless. So we had to take the codec apart and build it newly in a stateless way with a stateless API, which is mainly also taking out the whole reference frame handling, because codecs normally do that on their own. But in Vulkan Video, you have the full power over that. So we, if we want to plug in a different codec, we need to adapt it heavily. This is the problematic part of this project. And the last point was that we wanted to have a direct image buffer access between the codec and Lavapipe to have zero copy there. Finally, after we built it, we had to evaluate it. And here, we need to check it for both. Is it compliant to the Vulkan specification? And is it complying to the video encoding standards? And therefore, we had simple functionality tests using the sample codes from NVIDIA. Also, we have a simple video encoding sample on GitHub, which is roughly 1,000 lines of code to show you how to use Vulkan Video encode. And for decode, we have also about 1,000 lines sample, which is far away from NVIDIA's perfect every hardware and codec sample. It's but for easy understanding. And for checking the conformance, we mainly use the conformance test suite. The Vulkan conformance test suite is thought to check drivers, and as we extended a driver, it was the perfect match. It's available for Windows and Linux. I assume also for Android, but we did not work on Android. And the number of tests for video are growing. And it was also a good source for examples for video. So you can also look into the conformance test suite to have good examples for using the Vulkan API for video and for other parts also. And finally, it worked out. The good thing is we used the Vienna Vulkan engine with this Vulkan video support, and we did not need to adapt the application, of course. We just replaced the driver, and it completely worked on CPU, no hardware anymore necessary, and could produce H.264 video out of the rendered graphics, which is compliant. You can run it in, view it in a standard video player. And also the conformance test suite said, okay, for all supported features, which is only a subset, of course, we have full compliance. And what does the conformance test suite also do is check if it can decode the video again and if it matches the original video. You can not exactly pixel by pixel compare it, but it compares it with signal to noise ratio comparison. And also here we fulfill the requirements. So the outcome of my work is that we have now completely CPU-based H.264 encoding with an Vulkan Video API running in Lavapipe. You can use it either with the LLVM pipe rasterizer, but you can also use it with another video source or as a second Vulkan device. So you can have one Vulkan device without video support to render your graphics and then use the Lavapipe driver to do the encoding. But there's much work to do, still to do. We do not have video decode yet there. We would need to extend it to have more features, other profiles. Also, the performance was not evaluated yet, but this depends on the codec and not really on our part of the implementation. Where we come to, we would also like to plug in other codecs. So we're interested in people knowing codecs which have stateless APIs and which also from the license match to Mesa, because a good option would be X264, but it's GPL, and Mesa is MIT as far as I know. So we have here a license problem. And finally, the plan is to get this upstream into Mesa as soon as we have really good support for all these features. So this was my thesis, and I'm open for questions.
Thank you.
Hi, sorry, this is a question for a comment and a question for the professor, if that's all right. So the comment is just that thank you for giving such a detailed breakdown on how to teach and make Vulkan more accessible to students. For a bit of background, I did my bachelor's at DigiPen, so I know that working with graphics is already an incredible thing to do. For a student, you have to squeeze so much time. So for the professor and for anyone who's making Vulkan more accessible, thank you very much, because this was a nightmare when I was making my video game engine. And yeah, for the question, I'm basically asking what's the cost of implementing the course? Because from what I've seen, you already have so many students who know how to use Vulkan. So I imagine finding TAs to help you out with helping the students must be pretty easy. But not every university has a bunch of students who are already proficient with Vulkan. So how many TAs do I need? How much time do you need to train people to use Vulkan?
I do this by myself, 100%.
No TAs?
Well, I have tutors and I have people checking on the submissions.
Oh.
Okay, but concerning all the content and the engine and adapting all the stuff, that I do that myself. I think it helps me to understand Vulkan, you know. I want to teach things that I really know. That's why I do it myself.
Oh, that's impressive. Can I ask about man hours then?
many years.
Okay,
many years of thinking. Yeah.
Thank you very much.
Yeah, and a question for you as well is, I imagine you've gathered some really interesting data in teaching Vulkan over that period of time. I'd be really curious, the feedback from your students you've collected, what particular things they struggled with Vulkan specifically? So not graphics, but what Vulkan concepts or ideas did they struggle with?
Concepts and ideas. I think it's not a single concept. It's just the amount of volume. And usually what I see is when they submit their work, then I see whether it works or not. And I see also the progress towards the next submission. And what you see then are the problems that pop up in the forum. So usually this, because the tasks are very specific, you know, you have like 3 tasks and they very, like, I don't know, change this in the tutorial to this, you know, or enable to creating one more object or something like that. And what people struggle with is very mundane. It's to getting to run on Linux, to get it to run on Mac, to get it to run on very ancient hardware. These are the typical problems they struggle with. Otherwise, I think if you split it up into very small chunks, it's manageable, and you really have to focus on this core that enable everybody to build on top of that. But it's a good question. Thank you.
When you were encoding H.264 on that CPU, I noticed that you were able to achieve 20 frames per second. I didn't know what your pixel dimensions were and what CPUs you tested that with to get that 20 frames per second. I was just curious about that.
We did not do really performance comparisons yet. So what you have seen on the screenshot is most probably running on an Intel 10th generation, because this is my desktop CPU. Yeah, so I cannot really say about the performance yet, because the interesting part was is it possible to get this in the Lavapipe driver at all and get the Vulkan API working? Improving the performance of the codec was not the main intent yet. And I know that Mini H.264 has handcrafted assembler code available for different platforms. But what I mainly used was the C implementation. So we can get better just by improving the codec, which we plug into this Lavapipe API here.
Thank you.
Thank you for moving forward software rasterization and for your presentation, of course. My question was, when you chose your code base and chose Lavapipe, did you compare with other well-known software rasterizer like Sys Shader? And if you did, why did you choose Lavapipe? Thank you.
The reason to choose Lavapipe was I looked shortly into Swift Shader and into Lavapipe, and for me it looked like Lavapipe is more maintained. It's there are people actually maintaining it. It recently even got Vulkan 1.4 compliance tested, so it's in the compliance database of Vulkan. So this was the main reason.
Any other questions? Yep.
Firstly, thank you for teaching Vulkan. Is Khronos and the Khronos members doing enough to support you with information or other support? If there was one thing that you could ask from Khronos, what would it be to help you?
I had this discussion with Marty early on. I think what would be very helpful is to guide people through the specifications better, maybe in a graphical way, to make more available and obvious what has changed and why this makes sense, and how the different versions of the calls, like from the initial call to the second version and so on, what has changed in a shorter overview. That would be very helpful. Otherwise, I think the documentation is very good. It's very big, of course. I think it's not easy for students or newcomers to go through all the docs from top to bottom. So everything that boils it down to more manageable sizes is good. But we go in the lecture, we go through that anyway in a pace that I think can be digested, and then you can point them to the various points. But as I said, having a little bit more overview about the evolvement of extensions and calls, that would be helpful.
Any more questions before we break for lunch? Okay, one last round of applause for our presenters.